Okay, hello everyone. Welcome to join Space Observations and the Sustainability course today. Today's lecture is Professor Chao-Hung. He is from Department of Geomatics and from National Cheng Kung University. His research interests are 3D point cloud modeling, computer graphics, and digital geometry processing, geospatial information visualization, and analysis, and remote sensing satellites. Okay, Professor Lin, please.
Okay, I share my screen. Thank you for introduction. And the first one I have shared. You can download the slide and also the example code of this lecture. The link is posted in the chat room. So could you give me a message in case that you already successfully download the documents? Because this lecture we will use some demonstrates. Even we'll teach you how to train the deep learning model, or call it ALN model, by yourself. Then the code is inside the link. So please download the document from the link. And before that, maybe I need to introduce by myself. Now currently I serve as a professor in Department of Geomatics, National Cheng Kung University, and my lab is a Geo AI lab. So most of my research is about deep learning on geospatial data containing satellite image, UAV image, and also LiDAR point cloud. So here is the link containing the slides and code. Okay, at the same time, in this lecture, you will learn the concept of deep learning. Maybe we can call it the artificial neural network. It's an extension of ANN. And in this lecture, you will learn how to build ANN models by using TensorFlow and Google Colab. Then actually, we will use the Keras is built on TensorFlow. Another one, you also will learn how to train ANN models. In this lecture, we will see examples containing fully connected the neural network for a very public dataset called a NIST. The dataset here is for image classification, and this dataset is in general is for beginner, for deep learning beginner. Now another second example is the convolution neural network for another dataset called Cypher-10. This dataset in general is used in the image classification competition. The third example is a quite important model called autoencoder. That then in this example we demonstrate how to use autoencoder for image denoising. That is in the file here, show here. So in total, you will have three examples in this lecture. Okay, so because this lecture we have some hand-on practice to build a model, to train a model. Then we need the tool, the platform to help you do that. Then the platform I choose is the Google Colab. And this platform is basically free deep learning environment running in Google Cloud. So it's in the Google Cloud, but not in the client. And why it's a basically free is because for they provide the the deep learning computation environment, including the GPU computation resource for users. And it's a similar like with limited resource. It's similar like the Gmail. It's a free for general users with limited capacity. But it's good enough for most of the users, especially for deep learning beginners. And the environment, the deep learning environment already installed most of the package you need, including the TensorFlow, Keras, NumPy, and Matplotlib. Those are the package we will use in this lecture. And in general, in case that you would like to install the environment, the deep learning environment in your computer, in general, you will take maybe the 1 day to install all of the driver, containing the GPU car driver, containing the CUDA driver, and also the Python and other package. It actually takes time to do that. But now currently the Google provide the Colab for us. It will be easier to use that. Also provide free GPU computing with a professional GPU car for the best users. Then it's actually the GPU car, the professional GPU car is quite expensive. So here, the first step is to install the Google Colab. They contain several steps. It's not complicated. I go through quickly. It's several steps shown here. I will explain step by step. So before we move to the lecture, the first thing for you to is to install the Google Colab. Before that, the first thing you need to do is to have the Google account. I hope you already received the information that this lecture, the one of requirement is to have the Google account. So the first thing is to log in your Google Drive. Then my system is in Chinese. I did not have the English version system, but it's not difficult for you to recognize the position. The interface are the same with yours. So here is the interface of Google Drive, and then here you can find the applications you have. Then here show more. Then we click here to install the Colab application. So when you click here, you will turn to this page. Then this page lists all of the Google applications. Then here is a search text box. You can to type the keyword here to search for the Colab. So we can tap Colabatory here to search the Colab. And then you will move to this page. Okay, it will be hard for you to do it step by step. So I provide the slides here. Then I will you have time to install the Google Colab. So here is a button to install this application. So click this button to install the Colab. Then the step 5 is upload the code to your Google Drive. So you can get the code from the link I provide in the chat room. Three codes. So this step is double click the code here. You upload to your Google Drive. Then you will move to, you will open the Colab. It's a new page. And here is show the interface of Colab. Then the final step, had a button here, the button of run the code. So you can try to execute the code and to try to read out in case that you can successfully run the code. It means all the environment you already setting up and you can to run the code here. Okay, I think I will stop here and maybe wait for 10 minutes. Around 10 minutes, you can install the Google Colab step by step. And again, in case that you already finish the installation, let me know. You can send a short message to me. Or you have any kind of questions, you also can send a question to me on the chat room. Then here, I cannot demonstrate the process because in my Google account I already installed a Google Colab. So so the way I can do is to here to show you the step by step, and you need to do it by yourself. Okay, let's start to install the Google Colab. Somehow it will be easier. It will be easier for you in case that you have double screen. The one screen is the Google Meet. The another screen is you can process the installation. So I'll show you again the process. Here I already is my Google Drive. It's my Google Drive. Then here is a button. And this button show the application you have. Here is the Google application you have. And in case that you did not have you not install the Colab yet, then you can add more. Here is to linking for more applications. Here, the button here. Then you will move to this page. It's a Google Workspace Marketplace. Then here, the text box here to search for the application you want to install. So you can search for Google Colab here. So here is show that I already installed. Then you have the button here. You will have button here to install the application. In case that you already install the Colab, send a message to me. Then we have three example codes. then you can upload the code to your Google Drive. Then simply to double click the document. So here is Keras and NIST IPyNB. You double click the document, then you download to move into the Google Colab. So the page you will direct one, the code here, and here is their button. The button is something like the button with the icon of the play. There is to execute the code here, so you can execute the code. Now it means you now allocate the GPU and also the client, the disk memory to you, and it start running. Here's the being start running, and you can move to the end of the code, and now it's to download the data set. It means you can successfully to run the code. And here the some sort of information of the code of the model training. I will introduce you later. Okay, some of the members already installed the Colab. And now we move to the slides. We have some more package for the Colab. The first one, it provides the GPU computing. So you can use the GPU. You can change from CPU computing to GPU computing. The setting is here to change the running style. So here the selection from RAM from CPU to GPU, and click the button here. Is another information for Colab. Then after you execute the example code, you can find the result of the, here is show the model training, and then it's the reported result. Okay, then we move to the concept of the deep learning. The deep learning belong to one branch of the machine learning. And here is a list of all machine learning techniques, including the regression, including the Keras, the neighbors, random forest, the Gaussian mitchell models for the meta machine. And so we can classify those methods to be the traditional supervised machine learning method. And lots of the study already reported that the deep learning algorithm outperform the traditional machine learning algorithm as the increasing of the training data set. So in the Google brand team, to explain why deep learning is why deep learning is better than other machine learning, and why deep learning is now taking off to fly farther. It used the rocket to minute the deep learning, which contain the two components, engine and fuel. The engine linking to the neural network, then fuel linking to label data. So in case that you have the big engine, but on a small few, you can not able to reach the orbit. And in case that you have small engine and a lot of fuel, you can even take off. So both our engine and fuel is quite important to rocket and also quite important to deep learning. The engine here linking to the deep neural network, and fuel linking to the big data. So in case that you had a big data, such as in the field of the remote sensing, we have a lot of different platforms. We can have a satellite platform. We can have the alien and the UAV platform, even a cell phone. Also, we have a lot of different sensors, from RGB sensor, multispectrum sensor to LiDAR sensor. So without a doubt, we have a lot of the application based on the platform and sensors. And here is some example for UAV platform and sensors. Also, lots of the satellite and satellite images. Here is to show the some sort of applications for that kind of data set. So it's a big data for the remote sensing field, and so the deep learning should be the good tool or technology to solve some sort of deep learning problem. You would like to make your remote sensing system to be the automatic or semi-automatic, or you can say you would like to make your remote sensing system to be the smart, and it will be suitable to use to apply the deep learning technology to your system. The artificial neural network of deep learning can simplify to 3 steps. It's not only for NN, not only for deep learning, but also for other machine learning methods. Here is a 3-step: define a set of functions. Then the step 2 is to define the goodness of function. And step 3 is pick the best function. I will introduce step by step. Then here, the step 1 is a mean to define a neural network. So we start from biological, the neural system, especially the brain, the neural system. They contain a lot of the neurons. Here is the neurons. We have the dendrites, the branch, small branch. Here is a dendrites or neuron to receive signal, to receive information. And those the information and signal integrate to a neuron and output to next the neuron. This is the biological neuron. And here is a numerical neuron. The input, here's the input from A1 to AK are the inputs to neuron. The link with weights on the link. So the integration of the input is the linear combination of input with weights plus the BIOS. Here is BIOS. The equation shown here. The Z is the linear combination of inputs with weights. And the Z will pass through a function called activation function. Then the activation function is the nonlinear function. So we'll make the neural to be the nonlinear small system. Between the input and output, it will be the nonlinear system. Then the activation function is something like you know that the neuron is not always active. In case that the information is not strong enough, the neuron will not active. Then it will control by activation function. So in case that Z is strong enough, the activation the new node will active. Then it's controlled by the activation function. So then here is the new node. The input to the new node can be the output from the new nodes. Then the output of this new node can be the input of other new node. So here, a neural network is a different connection lead to different neural structure. And here is the neural structure. The key part here, when we said that we train a model. Now that we train a model, it means that we solve we find the optimal parameters inside the model. So the key part is what is the parameters inside the egghead model. The unknown parameter are all the weights on the connection, and all the BIOS attached on the new node. So here, the weights from W1 to WK and the BIOS from B1 to BT are the unknown parameter in the new node. When we training the model by using the training data set, it means we use a training data set to solve those unknown weights and unknown BIOS. Okay, any question here? Any questions are welcome. You can to stop me, or you can directly to send me your question. Okay, we move to the next page. Here I show you a toy example, simple example. Toy example means simple example. Here two inputs and 3 layers, 2 new nodes in each layer. And in case that the input is 1 and -1, we also already have the weights, and the BIOS is another 2 weights and the BIOS. So here we can to calculate the output. Here is a 1 time 1 plus here time here plus BIOS 1. We can obtain 4, right? And here we have activation function in case that we use the sigmoid function. Here is the equation of sigmoid function, and here is the curve of this function. The input is 4, the output will be 0.98. Here is the output of this neuron. It's the same process of this neuron. The output will be 0.12. The same process, 1 times by -1 plus -1 times by 1 plus 0. Then pass through the sigmoid function. Then the output of this layer to be the input of next layer. Then we can further get the output of these 2 neurons, and also the output of these 2 neurons. This is the data process of the neural network. I show you another example, the similar process. So when we regard the neural structure to be the function, here is a function with the unknown weights and BIOS. And the input is a vector, the output is a vector. We can simply to represent the process by this equation. The vector input to function, the output is another vector. We input another vector to function, we got another output. So setting up a neural structure means to define a set function, a function set, a set of functions, and then functions contain a function contain different weight and BIOS. So the whole neural structure will look like this one. Here is the input layer. Then here is output layer. You have several hidden layers. Then circle here is to represent a neuron. And we can, in general, we represent the unknown weights in a matrix. We call it W1 here. Then we represent all the BIOS here in a vector. We call it B1 here. Then it's a similar in this region, the matrix W and BIOS B2 and so on. So input is a vector. We call it S. It's a vector containing all the components from S1 to Sn. The input to this layer, it will be S times by matrix W plus vector B, and paying through activation function sigma. The output of activation function is another vector, we call it A1. And this vector to pass through another layer, it will be times by matrix W2 plus BIOS B, pass through activation function. The output will be another vector called A2. So it will be this kind of process. And output, the final output is Y. So we can simplify the process by this equation. Input to the function f, and output is Y vector. Then when we would like to look into the function f, what is the content in function f? In function f, it is that kind of component. Will be the vector multiplied by a matrix, then plus the vector. So a lot of the matrix multiplication and vector addition, it will be a lot. You can use parallel computing to speed up the matrix operation. In general, the unknown parameters inside a deep learning model will be a lot. It's not only several. It will be millions, 2 million, 3 million will be millions. Currently, the model is much bigger than billions. It will be billions. It will be billions. So the computation cost is extremely high. It's a need to use a parallel computing to help you to speed up the process. So here is a hidden layer, input layer, and output layer. And you can find that each neuron fully connected all neurons in the next layer and previous layer. And this kinds of the neural structure, we call it fully connected the network. It's the first, in general, is the first neural structure you will learn in ANN course or in the deep learning course. The fully connected neural the network. The forehand, you call it feed-forward fully connected network. And deep model or deep learning mean you have many hidden layers. It simply means you have many hidden layers. So in case that we have the task is a handwritten digit recognition, then the input the image of the kinds of task is like that one. It's an image. and it's a digit 2 inside the image. The input to the model is an image like that one, a small size, 28 by 28 pixels. Then we will flat the image to be the one-dimensional vector, flat one row by one row. So it will flat into from 28 by 28 to 784 pixels in one vector, in one column. That is the input to neural, to NN model. Then the output will be 10 neurons, 10 outputs, or 10 floats, represent the probability of the digit O, from digit O, digit 1, digit 2 to digit 9. The probability of Keras. Then here you have the highest value. It means the image is digit 2. So here the output, that means the probability of Keras. So okay, I skip here. So here is the step 1, define your neural network. And step 2 is define the goodness of function. The step 2, in case that you already have an NN model, and you give a set of parameters inside a set of parameters. And also you have the training data set. The training data set is you, in case of the image recognition, is an image with label. Here, the image with his ground truth. So with the ground truth, you have the target. It's 10 outputs, the 10 value represent the probability of the classes. So here, the probability will be 1, and other position will be 0. Then another one, the image will be the input of the neural. You will get the output of this input. The Y1 to Y10 is the output of neural, and we call it Y. And the ground truth, we use Y hat. The difference between the output and ground truth is called the loss of this training data. The loss is defined as the difference between Y and Y hat. You can use any kind of function to be the loss function. You can use the mean square error. You can use the cross entropy. In general, for the classification, we use a cross entropy. The performance will be better than the mean square error. I don't have time to explain that. You can Google it for more information on the loss function. So the goodness of the function is the mean. Here define the function to represent the difference between Y and Y hat. And for all the training data, you will have a larger amount of training data. And training data is mean data with ground truth. So the data input to the model, you can get the outputs. Because you have ground truth, you can get the loss, the difference between Y1 and Y1 hat. You have more data, more data input to the model, you can get the loss. The summation of the loss can help you to find, to minimize, to find the best function in function set. It means to minimize the total loss, to find the best the optimal function in the function set. That means to find the optimal parameters, unknown parameters in your neural, they minimize the total loss. So the third step is to pick the best function. Is mean to based on the goodness of function to pick the best one. The first one is that you have a set of functions, a set of parameters, and the step 2 is to evaluate the goodness of the parameters. And step 3 is to pick the best function. And the best function is the optimization function, optimization method. In the deep learning, it's based on the gradient descent. I simply use this figure to explain what is gradient descent. The y-axis is the loss. Then x-axis is unknown parameters. The unknown parameters. So this step is to find the minimal of the loss function. The minimal will appear here is a minimal loss. And because we have a lot of the unknown parameter, initially we need to give a initial value of unknown parameter. Assume that the initial value here. And based on the loss function, we calculate the gradient. The gradient is the direction to the minimal. The direction to the minimal. With this direction, we can move toward the minimal. Then gradually, it will move to the minimal position. It's a gradient descent. So all the unknown will start in the vector containing the weights, all the weights and bias. We will assign an initial value to each unknown parameter. Then calculate its gradient. And with the gradient, we update the parameter. Then calculate the gradient again. Then update the parameter. It's that kind of process. It's an iteration process. The update unknown parameter based on the gradient. The best concept of gradient descent. Okay, any question here? The questions here. So until now, it's fine. It's fine for you. Okay, you got a concept of deep learning. Okay, thank you, Abi. So we will use the first example, and is your hello world of the deep learning. You know, when you learn a new programming language, the first example you practice is a print hello world, the string hello world on the screen. So this example will be your deep learning hello world. And the package we use TensorFlow. Is a compilation of tensor and flow. So it's tensor is the dimension of the multiple dimensional data. Flow is the data flow. So it's the data flow in the neural. And the TensorFlow is developed by Google Brain, released in 2050. So now currently it's a free open source software used for the machine learning applications. And but we will not directly use the TensorFlow. We will use a high-level API of TensorFlow called Keras. Easy to use, then it will easier to build up a model and train a model in hours, even in the minutes. So the Keras is running on TensorFlow. Then Then TensorFlow is running on some computing resource, such as the CPU, GPU, even the TPU. So here is a short introduction to Keras. It's a high-level API written in Python and running on top of TensorFlow, even on other deep learning package such as CNTK, Ciano. It's a user-friendly, minimize the number of user action and multiple platform and multiple backend, the easy extensibility. So it's quite good for beginner. Then the data set you use is a NIST. The data set is a like that one. It's the data set from digit 0 to 9. They contain 2 sub data set. It have 60,000 training image made by one group and 10,000 testing image made by another group. Training image means you use this data set to train your model. Then the model evaluates or tests on the testing data set. And each image is grade level image and small size, 28 by 28 pixels. This is the data set. So the workflow of model training is that one. You have training data image with label. Then this label, this ground truth, is the integer. Then the image is a small one, 28 by 28. And because the input is a one-dimensional vector, one-dimensional tensor, so the thing here is to reshape the image from two-dimensional tensor to one-dimensional tensor. Then for the label here is the integer. Then you need use the one-hot encoding to transfer from integer to code containing 2 floats represent the probability. Then use cross entropy to the loss. So you design the network here by yourself, and to set the size of the input tensor is a 784. The size of output is 10 neurons. Okay, here is the whole structure. Then the Keras provides 3 modeling styles: the sequential model, functional API, and model subclassing. Then in this example, we will use the first the model building sequential model, quite simple input, simple output. The network would like one layer by one layer. It will good for more than 80 cases. So in case that the neural like leg one input layer, one output layer, 2 hidden layers. And now we would like to build this block. We decline a sequential object called model. And use this model to add 1 layer called dense layer. Dense layer is mean the fully connected layer. Then some parameter need to provide, including input dimension is 784, linking to the number here, 784. I use the point, will be easier for you. Here. Then the units is 500. 500, linking to the number of the neurons in this hidden layer. And also provide activation function. We use a small activation. And now to build the second block, the number of neurons is 500. neurons linking to the number of the neurons in this hidden layer. Also assign activation function such as SIMOE. And we build a sub-block. It's a 10 neurons, also fully connected layer. The activation function, we will use another called sock mask. So it's a process to build the neural structure like that one. Okay. And another one, we explain that we minimize the total loss to obtain the optimal parameters. But the problem, the one problem here is actually in case that you have professional the GPU card, the memory in GPU card is limited. Such in case that you use the Colab, then the GPU card in Colab you have is 11 gigabyte the memory. So the resource in the memory resource in GPU card is limited. It's somehow impossible to put all the training set into the GPU card memory. So you will use a mini batch, grouping your training data set to a group, we call it batch. So we do not really minimize the total loss, but minimize the mini batch. The process would like one, the rendering initialize the network parameters. Then the select the first batch. In this example, they containing 2 training samples. They use the 20 rows to update the parameter. Then select the second patch, calculate the total loss of the second patch, second examples. They update the parameter again until all mini batch have been picked, have been selected. The whole process is called one epoch. So you will repeat the above process until converge. This is the process of training. In the Keras, we use the function fit to train the model, provide training data set, provide the label, and also to set some parameters, including batch size, how many samples in mini batch, and provide the number of the epoch, or is equal to 5, it means repeat 5 times the process, this process. Okay. So any question here? Until now, do you have a question? Because I have a double screen. When I look at this direction, it means I look the chat room to see any response from you. Okay, in case you, we will move to the Colab. And so now you move to your Google Drive. And hopefully you already download the document, download the code and upload the code to your Google Drive. Then you can click the first example code, Keras, and list this one. Okay, this one, Keras and list. Double click. Then you will move into the Colab, the platform of Colab. Then I already excuse run the code, and we can check the result here at the bottom of the code. Here message is showing you are download a data set from this link. And this key link is a NIST data set. Then I showed some sort of example, some sort of information on this data set. The number of training is 60,000. Number of testing 10,000. The image is shown here. Then the model structure shown here. One dense layer, another dense layer. The total unknown parameters is 0.2 million. Then the start training is the ePart, the first ePart. Then show the accuracy. Then validation loss. Here is a loss. Then here is accuracy. So you can see that the loss is a decrease, the accuracy increase. Then we print in the figure, it would look like that one. Here is a training, the training history. That the two curve. Here this curve is a training curve. And here is a validation curve. And then SS is ePart. Then YS is accuracy. It's a similar figure. The y-axis is the loss. So you can to check the convergence of your model from this curve. You can find it gradually decrease, then converge. So here the ePart is somehow not enough. You need more ePart to make more converge. Then the final accuracy is 92%. Here is for testing. The 92.1%, the testing accuracy. And for this example, the thing you can do is to provide more eParts. Okay, and here you can find it. Here is the model. Two dense layer. Then model training is here. Then here you have one important parameter is a ePart. You need more ePart. So here you can change it to 10. Then another one, here is a GPU computing. Even you provide a TPU computing more faster than GPU. So we can run the code again. Then here is show some information of your resource, computing resource. You have the computer, the RAM is 12 gigabytes of RAM, and also the how many disks you have. Okay, you already finished. We can check. So now it more converge. So actually you can steer to increase to add more eParts to train the model, right? Then another one you can change is to change the activation function. You still have some activation function you can use. Now we can change to redo and to click again. The redo activation have the advantage to avoid gradient manage. The gradient manage is the big problem in deep model training. Compare with the soft math. you have advantage of avoiding gradient manage, and also have a better training result. So you can find that it's a new training. Then so for training, the accuracy is 99%. And for testing is 95%. The better than red, but better than Simoy. Also, another thing you can do is then here this lecture is a deep learning. How to make the model to be the deep is quite easy. Just copy and paste. So you copy here and paste. So you already create one more hidden layer. Then change it to ReLU. So you can assign the number of the neurons, such as it's 60 neurons in this hidden layer, right? In case that you would like to more hidden layer, how to do it? Copy and paste. So you will have a lot of the hidden layer, right? You have many hidden layer. But because here we have a lot of time to train the model and remove some sort of hidden layer, and we train the model again. Okay, currently here is the number of unknown parameter. It's a 0.2 million unknown parameters and 10 epoch. Here is the training accuracy, the accuracy and the loss. Then the testing data set is 94.9%, so it's not improved. And you can tune your model to get a better performance, such as now you would like to use all the training data. You like to use all the training data. Now I only use some sort of training data here. Here you can use all the training data. And also you can use a more epoch, such as 20 epoch, the large batch size, 32 batch size, to tune some sort of hyperparameter, and to design suitable the neural structure that it will fit with your task. Okay, any questions here? I think it's a time to take a break, and let us take a 10-minute break. Also, at the same time, you can welcome for questions. Do you successfully run this code? Could you send a message in case you already already have the result of this example? Or Kevin? Okay. How about Kevin? You also can to tune the hyperparameters, or you also can to redesign the neurons, the network, to check what the result you get. Then we move to the second topic, is a convolutional neural network. This topic with example, second example, and here this is the neural network you need to learn. The most of the deep learning model, maybe more than 90% of deep learning model contain contain the CNN structure. So it's the reason you need to learn the convolution neural network. But the problem here is the first one you need to understand. Before that, you need to understand what is a convolution. What is a convolution? I use the show animation to explain the meaning of the convolution. In the example, they have the two objects displayed by different color, red rectangle and blue rectangle. The blue rectangle is dead there, did not move. Red rectangle move from left to right gradually, right? And in this case, the blue rectangle represents an image. And the right rectangle is represent a mask, or call it filter, convolution filter. It will be the small size of the page. Such as here is only 3 by 3, a small one. And here they have the yellow region. You can find that it's an overlapping of these two objects, right? The yellow region. Then the yellow region will be the output of the convolution. So the black line here is the convolution result. Convolution of these two functions. So in general, from equation, the equation you saw is this kind of equation. The convolution between convolution of these two functions. So it's an integral here. Your integral is the mean. Now it calculate the yellow region. Then here represent the image. Here is represent the mask. I also use the color to represent that. It's a convolution. In the image case, I use several simple examples to make you understand how convolution perform in the mask, in the image. And here is a small image, only 6 by 6, two values, 0 and 1, and a small field size, 3 by 3. They have the coefficient in the filter. I use the dot. Then the filter move to the image here, then perform the convolution. And perform convolution is an element-wise multiplication, the integration of element-wise multiplication. The output will be -1. The first place here tied by first place here, plus the second place tied by the second place here. Is the pixel-wise multiplication and integrates all results. So the calculation I show here, the output of convolution will be -1. Then move to next pixel, perform convolution again. The output is a -1. The calculation inside is here. I show here. It's also integration of pixel-wise multiplication. Then finish this door, move to the next door. And finally, is a convolution result. So the filter move over the image, perform convolution at each pixel. Is a convolution on an image. Now, another one need to notice is here is output 3. The largest response during the convolution. then you can find that it's a position mapping to the image is positioned here. And so you can observe the filter. They have the edge here. This means this filter have the function of the vertical edge detection. It can able to detect the vertical edge. I show you an example. Here is the image. Here is the image. Then I use this filter to perform convolution on the image. And here's the result. The output of this spatial filtering is only the strong vertical edge. Strong vertical edge here. Another convolution example, which I changed the filter to this one, and perform the convolution. So here is the process of convolution. Also, you can find that here you have the edge in your filter. So you have the strong response on these two positions. It's because here you have the edge here. Then this filter is able to detect the diagonal edge. I show you another example. In case that we use this filter, we use this filter. Then the diagonal edge will be enhanced. In case that we change it to this filter, then horizontal edge will be enhanced. So this kind of convolution have a function to extract directional features, directional edge features from image. It also is the edge feature respond to high frequency component of image. It also able to extract low frequency component of image. So any question here? Then the whole standard CNN will like one. From image, we perform the convolution layer. We add a convolution layer. And in general, we after convolution we have the pooling layer. I will explain that later. Then another convolution layer, another pooling layer. They can repeat many times to make the model to be the deep. Then flat to be one-dimensional better, fed into the fully connected neural network, and the output result. This example is to estimate the chlorophyll concentration from optical satellite image. And this is the standard CNN, but currently it is not mean you need to follow this structure. I still can any kind of structure. So currently, actually, now we not always follow this standard CNN, such as you can remove the fully connected layer. You can add more convolution layer here. Even you can move the pooling layer. You can design on the neural structure by yourself. I use this example to explain how to process, the workflow of the CNN in the structure of the neural network. The same example, 6x6 image. 3x3 filter, and this is the result from this filter. So here we have the input of the NN model, and you can see that this 3 pixel mapping to here, and this 3 pixel mapping to here. Also, this 3 pixel mapping to here. It's because the 6x6 image, 2-dimensional image, flat to a 1-dimensional tensor vector, like that one. Then the output to the next layer is 3, right? And in total, only 9 connections to this neuron, not fully connected. Only 9 connections, right? Here is a perform convolution here. Convolution here is mean the element, the pixel-wise multiplication, and integrates all the multiplication. In total, they have the 9 multiplications, 9 connections, and I use the color to represent the weight of the connection. And this connection is a mapping to here, the weight 1. The connection mapping to here, the weight -1. I clean the draw here. And, so 9 connections. So after the convolution, the output is 3. So only 9 connections, not fully connected. And because it's not fully connected, you use less parameters than fully connected the layer. When you move to the next pixel, it perform the same thing. The output is a -1. The 9 connections. Connection to this 3 pixel, this 3 pixel, and another 3 pixel. You can see that I use the same color. Here is a red color. Here is a blue color. It's the same weight with the first neuron. So another advantage of CNN is the shear weight. Is the shear weight. Quite important in the CNN. The shear weight. The weights in this connection are the same with this connection. The weights in this connection are the same with this connection, the shear weights. So the parameter in the CNN layer are the coefficient in the filter. The unknown parameter in the CNN layer are the coefficients in filters. Then actually, the coefficient in the filter are the weights in the connection. So they use this the way it still need to the process is the same process of the neurons in the network. It use the same process to perform the convolution. It's a short comparison between the fully connected layer and convolution layer. Right-hand side is a fully connected layer. The input is 1-dimensional tensor. Then fully connected. The left-hand side convolution layer. The input is 2D tensor. After convolution layer, the output is a feature mat. We call it feature mat. That is a 2D tensors. Okay. And we move to the pooling. The pooling is quite simple. In a feature map, we have the two feature maps from the convolutions. Then we divide to a cell or divide to the pool with a fixed pool size, such as here is a 2x2 pool size. Then the division will look like that one. The 4 new nodes in the pool, 4 new nodes in the pool. Then mass pooling is to extract the mass value from each pool. The called mass pooling. So from here to here, it's a mass pooling. Then the mass pooling is mean the downsampling of the data set. You decrease the resolution or decrease the image size. It's a perform a downsampling. Then the flattening is to flat the 2D two-dimensional feature map to be the one-dimensional feature map, one-dimensional tensor. And flat one image by one image, or call it one feature map by one feature map. Here is a two feature map. You flat the first feature map connected with the second feature map. That is a flattening. So when you flat the feature map, then fit into the fully connected layer, that is a standard process of CNN. The structure will look like that one. Okay, it's a input. Again, it's a 28 by 28, one channel. And here is a design convolution layer with a 3 by 3 kernel. And here is a pooling. So the image size decreased from 42 by 42 to 12 by 12. Then another convolution layer, another pooling. Then flattening to be one-dimensional tensor. The dense layer to be the output layer. It is the standard structure of the CNN. Then for the CNN layer pooling, the purpose for that is extract features. Extract the feature, edge feature from image. Then the second part, the dense layer here is to regard a classifier, to classify the feature into classes, classes 0 to 9. So here regards a feature extraction, and dense layer regards a classifier. The input is a numerical data containing pixels, 28 by 28 pixels. Inside the image, inside here is only pixel value, so it's a set of value only. Then you put to after the convolution layer, the extraction is a label features such as the edge features, some edge features from the input. The second convolution layer is to extract feature from feature map. So we can simply call it high level features. It's a second convolution layer. And here is a regard is a recognition the content from high level feature. You can recognize the content from high level feature. It's the process of the CNN. Now, any questions here? The CNN, the process of CNN. Any questions? Do you understand? Already is to somehow too hard for you. Okay, we move to the second example. And you can move to your Google Drive. We have provided 3 examples, 3 codes. There is the second code. The name of the file is a CNN. The data set we use Cipher 10. The double click. I close. Then here is the code. Smaller. Okay. Now I will explain more in the code. Here is the import data set. The name of data set called Cipher 10. I show you what is a Cipher 10 here. Here is the Cipher 10 data set. It contains 80 million tiny image, 10 label, 10 classes, 10 classes. Here is 10 classes here. And as I mentioned, the Cipher 10 is one of the standard competition, the data set for image recognition. Another one is more complicated, the Cipher 100 classes. Then the data set is quite easy to use. You already provide in Keras. So it's simply to import from Keras directly to use the data set. So here we to load the data set to several array. Then here is to start the training image. Then here is the training, the label of training image, test image, label of test image in array. Then here is another array to store the name of the classes, the 10 classes. I define a function to print images. Here is a function to print image. Then initially I send 32 image to this function to print out. So when you run the code, is now initialize or allocate a resource to you. And now currently here is running the code. We move to now is the downloading the training data set. Cipher 10. Okay, here is the function. The image I show the 32 image here. Then move to the code. Now reshape the data set to 32 by 32 by 3. Then normalize the pixel value from 0 to 255 to 0 to 1. They can stabilize the model training. That means the pixel value is a grade level, and the pixel value is between 0 to 255. And we are normalized to 0 to 1. Then here is perform the one-hot encoding. Then design the model is a sequential model. And here at a convolution layer is a 2-dimensional convolution layer. And of course it provides a 1-dimensional convolution layer, 3-dimensional convolution layer. You assign the number of filters, assign the kernel size, assign the input shape, also activation function. And then add a pooling layer. you provide a pool size. It's a 2 by 2. Another convolution layer. Another pooling. Then flat to one-dimensional flat vector. Then the 2 dense layer. The number of neurons here. Then here is the neural structure. Then the send, I use a fit, the function of fit to train the model. Batch size is 32. Each part is 5. Then so here is a summarize the model in the table. The information of the layer, unknown parameters. Then in total is a 0.2 million unknown parameters. So here is the process, the accuracy, the loss. So not converging yet. It's not converging yet. The total accuracy, testing accuracy is not good enough. Only 67.8%. So the way you can do to prove the training is to more e-part, maybe 30 e-part. And you also can add more filters to more filters, or the more convolution layer, such as here. You can add more convolution layer and more filters. Right, another one. And you can run again. But this time, I guess you will take time because now it's a 38 part. Okay, so run again, and you can do it's a new structure. And now currently the number of the unknown parameter is 0.7 million. So increase from 0.2 million to 0.7 million. Oh, okay, the training quite fast. Now it's already the e-part number 5, number 6, around 6 seconds for one epoch. So it's now the training, and you can to check the number here, to check the accuracy, to check the convergence from accuracy, and also from the loss. So it should be the gradually decrease from the loss and gradually increase from accuracy. And you also can check the validation to check in case that to check the overfitting of the model, if the model is overfitting or not. Okay, I guess we wait a moment for the model training. So I think some of you not installed the Colab yet, even you did not have the Google account. And you can, to apply a Google account, install the Colab. Also to upload the example code to your Google Drive. Then you can train the model by yourself. And to train back, and also to modify the model and train the model by yourself. In general, in my task, in my research cases, the training of the one model takes hours at least. In general, it will take more than 10 hours in general, even several days. So it's quite important to have a good computing resource, the GPU computing resource. Okay, almost finished. Here I would like to show you this figure. Again, you find the y-axis accuracy. Then here, here is training in larger screen. Here is the training. Then here is the validation, the curve of validation. You can find it the accuracy of training increase, but the problem is the validation here is not increased as the training. So what happened to that? It means in this model, it already overfitting. The model already overfitting with the training data set. So one of the problems you need to solve is an overfitting problem in general. In addition to gradient manage problem, there are some of the training tips, training techniques help you to solve the overfitting. It's not belong to this lecture. I have the course in our department. It's a deep learning course. We have the topic is the topic of the deep learning deep model training around 6 hours, 2 weeks, to teach how to train deep model, how to solve the overfitting problem. You have some of the method to solve it. Okay, I think it's no problem to share the video. Not only for the last 3 classes, I think all the classes will upload video. I remember they have the course, the lecture. Already. The number of hidden layers, the number of neurons. Actually, you know, it's a process of try and error. So it depends on the output result. So it's why we always to tune the tune parameters. I call it hyperparameters. The hyperparameters are including the number of layers, the number of neurons. But also currently for the modeling problem, have lots of new papers published in these years. That the new methods to teach you the new methods to efficiently is to provide an efficient block for modeling. It means you can more efficiently to use the unknown parameters inside the model. So currently the new layer is not CNN at all. Before 3 years 3 years before, the CNN is popular, but now new layer called transformer is more popular than CNN. It's a new layer. And another some sort of study to study how to optimize the the neural structure. It also have some study to optimize your neural structure, or optimize the hyperparameters. Okay, other questions? We must move to the last topic, autoencoder, but I think I cannot finish it. So you still can run the code by yourself. And only deliver the best concept autoencoder. It's a quite popular model, concept, and method in deep learning. You know that during the machine learning, they have 3 different kinds of learning. Supervised learning, such as for prediction classification. It's a typical task in supervised learning. It belongs to the recognition. Then actually, the unsupervised learning is more important than supervised learning somehow in these years. It's a training model without levels. Some of the cases you have the data, but you did not have the levels. And unsupervised learning can use some specific task, such as clustering, style transfer is a typical example. Then unsupervised learning can use for generation to generate something that will be more difficult than recognition. Recognition is recognized here is an apple here, but generation is a generate unexisting subject, such as to generate a report, generate a song, something like that. Is much difficult than that. Then the autoencoder can apply to supervised learning, and also can apply to unsupervised learning. And develop of unsupervised learning is because of autoencoder. And because of autoencoder, we have the many new model, new paper methods on the unsupervised learning. And third one is more difficult than unsupervised learning, is reinforcement learning. It's a learning by himself. Actually, it's a model learning in an environment you create for them. Then can apply to a self-driving car. Then can apply to a gaming model. So such as AlphaGo and DeepMind, that kind of model is a training by using reinforcement learning. So actually, model training and model learning more important than modeling. Training and learning is a much important, more important than modeling. Another training technique include self-supervised learning, transfer learning. Is in between supervised and unsupervised. They also include a game. It's also very interesting training technique. Very, very interesting. Another one is called lifelong learning. So machine now currently already have the paper discussing the lifelong learning. It's the model you develop will continuously improve, continuously learning and learn and improve the performance. Okay, it's the whole structure of the learning, and the autoencoder can apply to this proof block, supervised and unsupervised. It contains 2 model, encoder and decoder. The encoder will encode to a small number of floats, much smaller than input. Then decoder is recover from code to the image, to the original data. Then these two model is the chain simultaneously, the chain together. So it will be look like this kind of structure. And I need to scale up some of the slides. They can very deep if I look like this kind of structure. And it is the unsupervised learning because the loss function is the output to make the output as close as possible to the input. So this kind of training don't need the label, only the input data. Then the purpose here is to extract the code. The original purpose is to reduce the data dimensionality, such as the PCA. And it's the paper here prove this way already is better than PCA. But in these 10 years, the autoencoder already applied to a lot of different applications. Then autoencoder can be the CNN autoencoder containing the encoder containing convolution and pooling, then decoder containing deconvolution and unpooling. So the deconvolution is the inverse process of convolution. Unpooling is the inverse process of pooling. Again, that moves the two images as close as possible. That is the CNN autoencoder. I skip some of the slides is deconvolution, and this slide is how to perform the unpooling. So here I would like to show you is the noise. Here you have the noise, the image, and you design an autoencoder. You would like to remove noise, but the problem is how to define the loss function. If you have the trip here, actually the input function, input image here, they add noise. The loss function is set to here to make it as close as possible. And then after model training, it use the model here only. So the input is a noise image, the output is a clear image. Here is an example I provide. It's on your now you can actually do not any requirement. Your laptop no need to have the GPU. Actually, it's a CPU is enough. You can use a CPU to run the code. But your laptop need to install some of the software package, including you need to install the Python and install the packages TensorFlow, Keras, the MetaLib, NumPy. Then you also need to install editor, code editor, such as the Python. You can use the Microsoft editor, is a Visual Code. You can use the Jupyter. Those editors are popular editor. And then another one, so it will take you some time to set up all the environments. Then you can run a code. Then to modify the format, the code format from IPMV to PY. PY is the extension file of the Python. So I think the the best way for beginner is to use the Colab, because the Colab already set up all the environment. So it's simply to install the Colab. I think it's the best way for the beginner. Otherwise, I think you will take at least 2 hours to install those software and packages. Okay, go back to here. It's a self-supervised learning. And here's input, then here is output. Also, the auto-encoding can apply to the segmentation. They can apply to alien image to extract the building and the road. They can apply to the SAR image to extract the oil split. They can apply to the point cloud to perform the segmentation. So currently, we also apply to point cloud to extract the ground point to generate the DEM. I demonstrate. Give me 1 minute. There is a third example, autoencoder. But I will not to. Okay, I need to train the model. Okay. Any questions? Can you understand today's lecture? Oh, it's difficult to understand. Actually, it's a course, 3 credit course in our department, but today only 2 hours. I just simply like to show you the third example code and also the result of this code. So you can find a converge wheel. And here is the original image. We add noise here. Then the model are able to recover from the noise image to this one. From here to here. And of course, it still can be improved. More layers, more parameters, new models to improve it. In case there's no question, is the end of my lecture. Thank you.
Thank you, Professor Yin. Thank you very much. And Yeou, please write down your answer for these 2 questions in Google Form. And if you have any question, you can also write down in this Google Form.
Okay, I got a question. It's about to see the parameters inside the model. Right? You like to see the question should be the unknown parameters. in the model or train the parameters. They have the Google have provided a tool called a TensorBoard. It's a visualization tool to show some of the information inside the model. Then one of the information is the coefficients inside. And that is quite powerful to use. I did not, I type in the chatbot, the name is called TensorBoard. And in general, we also would like to see the output of each layer, especially the CNN layer. And the TensorBoard can do that. It's able to do that. To see the output from the CNN layers.